I'd like to welcome you. Thank you. Thank you, Chris. Thank you, everyone, for being here. I have the privilege to be talking to you after the lunch, so hopefully that will make this presentation a bit easier, or not, we'll see. Anyway, I work at the Joint Research Center, which has as a mandate to serve society, stimulate innovation, and support legislation. It's a part of the European Commission dedicated on that. Now, to start with, you might be wondering, what is this guy talking about? He's talking about crop monitoring on Mars. Well, no. First of all, MAS is not, it might not be what you think. MAS is a clever acronym for what is now the Monitoring Agricultural Resources Unit at the Joint Research Center. And has nothing to do with Mars. It used to even be called the Monitoring Agriculture with Remote Sensing in the past. And now it has a more holistic name. And we still do quite some remote sensing, and I'll talk partly about that. Mostly, where I was working for the past 3 years was in using the Mars Crop Yield Forecasting System, or MCYFS, which is basically an operational service to provide agricultural intelligence for major crops over the EU and the pan-European environment, pan-European countries, in an idea to have a decision-making process on market intervention and policy support. Basically, what we do in Mars is provide numbers, generate numbers, estimates of what the total production might be in a given year. This is done on a national scale for each country in the EU, and we define areas of concern. All this as the season goes along, to provide a warning of what might be happening. This is consolidated in a bulletin that comes out every month. This goes, as I told you, to decision makers in Brussels mostly, but now also abroad as well. Now, the question of providing information on yield, and the idea is mostly yield that we deal with, the challenge is somehow summarized by this caricature, in which you have a farmer explaining to his son that, if we get enough rain and sun, and if it isn't killed by hail, and if it isn't damaged by frost, and if we get it before the snow, and etc., even if the grain handlers aren't on strike, etc., then we should get so much. As you see, this is not a simple task per se. Now, the way we deal with that, it might seem straightforward. Basically, we assume that crop yield is a function of the meteorological impact on crops, crop growth simulated parameters that we simulate in-house, satellite observations on crop vegetation, and the time trend of the past yields. The system to realize this is quite sophisticated and challenging, and summarized a bit more in this on this slide. So we start with the grid. We have this grid of 25 by 25 kilometers grid cells, in which we have weather data coming from, I think it's around 4,000 stations over Europe, which provide daily meteorological indicators that are interpolated to this grid. This is fed to a crop growth simulation model, which is specialized and run for different crops over Europe, and produces biophysical variables every 10 days. We also have satellite Earth observation imagery, and all of that serves as indicators that we can relate statistically to past yields at regional to national level. The output is quantitative analysis of the crop yield forecast that provides a quantitative analysis. This is driven by an expert system, in the sense that those who analyze and decide what to use are people trained in the unit and that are dedicated to a given country. We also do a qualitative analysis by looking at all these different sources, these different maps, to provide areas of concerns and as the season goes along. Now, about the current use of remote sensing for yield forecasting in Europe over what we're doing, we're mostly because this is my talk. I'll focus it essentially on the remote sensing part. We use an FFR product, the GRC FFR smoothed product from Lopez-Lozano at 1 kilometer, so pretty much it looks like that for a given decade. We aggregate this at subnational level using an arable land mass that is static based on Corinne land cover and or GLC 2000 outside Europe. And we have then therefore temporal profiles by regional profiles, at different administrative levels. A question is, when you know about how this works, is why are we still monitoring the landscape rather than the crop-specific field? With what we're doing, actually, with 1 kilometer data, we're essentially looking at a mixture. We're not looking at the crop-specific field. So the information sometimes comes from a specific crop. In some situations, you have the same crop zone over vast areas. But in most places in Europe, we have something more like that. And we're not getting information from the crop that we're looking at. Now, to answer that, another way to see it is also to pose the question of what are the ideal requirements for optical remote sensing data for our purposes in this system. We actually summarized this in a small communication in an ESA symposium 2 years ago. And basically, one of the main things that we need, in essence, for what we're doing is near real-time, high temporal frequency data. We need this new real-time information because we're working on in an operational system, and we're observing crop status as it is changing. And this can happen typically in the order of 7 days. You can have something in the growth season. This might happen in 7 days. So we want something with high temporal resolution in near real time. Many observations are discarded because of clouds. Many places in Europe, the weather is not so good, and we have, there's many reasons to discard information. And so we have a limitation and a trade-off between spatial and spectral resolution. In practice, what we're using is spot vegetation, sometimes AVHRR, MODIS, and perhaps POBAV, but we cannot, as is, use even the upcoming Sentinel-2 satellites because we don't have this spatial temporal resolution that is assured necessarily for now. And also, one thing that is usually good to remember is that, in principle, all individual observations should be available for us. Instead of using predefined composites, it's always a good thing to remember that maybe there's things that you can catch in this with high spatial frequency if you're not simplifying everything by a 10-day composite. Now, in practice, that is difficult. But from the research point of view and trying to develop new things, this is an important thing to remember, in my opinion. Now, there's the fact that we need an adequate spatial resolution to have a crop-specific signal. As I showed you before, these are landscapes of Europe, other types of landscapes in Europe, and this is typically the pixel we're using, which already the product that we get is, there are some bicubic interpolation things that go on in which the neighborhood comes into account. So basically we are observing the landscape, not the pixels. With MODIS, which you barely see here, but has this size over there, okay, sometimes you fit in the fields, but not always and not all the time. And basically, and so MODIS, as I will show a bit later, has a bit more potential, but we're still looking at the landscape. No? Another thing we need is a long-term warranty on data continuity. Basically, agencies managing optical EO instruments, they don't necessarily have always a long-term operational mandate. Meteorological satellites are an exception, but sometimes we cannot rely on chains that are developed for a satellite that might expire in 5 years. It's better for us. We're looking forward to something that's that you can have over a long time, and that you can build a long-term archive, because this is crucial for us. We're looking at information, comparing this year with the years before. As I said, not being sure that there's a continuity limits it limits the possibility to have to develop costly processing chains. Now then, another point is interoperability of products. It's a bit linked. We would prefer to have biophysical variables like FAPA or like LAI, and they need to be spatially and temporally consistent. We prefer this over ad hoc indices because these might not be available necessarily with a new sensor with different wave bands, etc. This allows the idea of having virtual constellations for a synergistic use of different multi-source data. Again, with the optic of perhaps continuing a long-term archive. Again, now we're in a situation in which perhaps the Sentinel-2-3 data with the GIO products that probably will be mentioned in this conference could start to have more of an adapted tool for that. But again, we need a crop-specific signal. So, some perspective for satellite remote sensing in Mars, moving towards the crop. The rest of my talk will be divided into two and maybe three if I have time parts. The first is an exploratory analysis of the current capacity of our remote sensing indicators that we use now to have a regional crop yield across Europe. Then I'll talk about a somehow innovative, unconventional method to use modest time series to retrieve a crop-specific signal. And then, if I have time, I'll talk a little bit about some ideas about better integration between our modeling and crop monitoring platforms in MAS. So, there. So, first question, in a way, what are the remote sensing indicators that we have? What are they actually indicating for us? Is it yield, really, that we see from the green biomass that we're monitoring? Or is it some other parameters related to yield but that are correlated or not? Or is it just changes in meteorological conditions that are not related to yield, for instance? Or exploratory analysis done mostly by colleague Raul Lopez consisted in taking subnational FAPAR time series across most of the NOTS 2 or 3 regions across Europe, which are sub-regional administrative units, let's say, and subnational yield time series that we have by collecting, that are available not always at the same degree of quality, but that are available across Europe. And what he did was to try and see the correlation between both by searching over this temporal profiles the optimum window in which he can accumulate FAPAR. And so basically, if you see on this graph plots an initial decade, and this is a final decade. These are the boundaries of this box. And over this box, he accumulates the FAPAR. And we see the correlation here, the correlation coefficient with respect to the historical time series. And you can see that actually you have some, so there are some places in which for a given region you have higher correlation than others. And this region, this spot can change from one place to the other. By doing that, we ensure that we're trying to get as much information as we can from the FAPAR profiles. And we can derive maps like that, in which here for wheat, what we have as a statistic wheat, we see the regression coefficient, the R-square, per region across Europe. And what you can see is that there's places in which it's working quite well. In Spain and Morocco, for instance, or in the Black Sea areas, we have R-squares above 0.8, which is quite good in general for this. Here, in Central, Northern Europe, often we have FAPAR is very poorly correlated to yield. So here, basically, the signal, the indicator, is not indicating anything about yield, and using it for that should be taken really with care. You see in this small map, I just put it next to it like that. Here you have the variation coefficient of the time series of yield. Basically, you see here in the green dots, which are very low values, that yield is very, very, the variation of yield from one year to the other is very low over this area. Here, it's much stronger. And of course, then you can understand to a certain extent that some places you should not try and get. I mean, it's not possible to go get very fine differences in yield in places where the signal won't be telling you anything. So, just to complement a bit this example, in Spain, for instance, well, you have some years with very low yields due to droughts, for instance, and so these. You can actually see, maybe not so well on this slide, not from here at least, that these curves, the curve representing these years, are much below the long-term average here in black. Whereas high yields often are related to green biomass as seen by the FABAR. Here in Germany, well, one bad year here and another bad year here have very different profiles, which are very difficult then to interpret and get a conclusion from that, from the analyst that has to do this in an operational way across Europe. We also extended this to barley and maize with different types of results. And I'll leave it on that. There's a poster on this that will be here. So if you have more questions about that, we can discuss it with more detail. It's just to give a picture of what can be done that we are doing at European scale. Now let's focus a bit more about going towards the crop-specific signal. So, crop monitoring with satellite remote sensing, well, we're basically, as I told you, based on a mixed signal for now, because the fields we're looking are smaller than 1 kilometer. There's quite a high variety of field sizes across the landscape, and you also have crop rotations along the time. You also have farmers that 1 year will split this field in two. And so one pattern from 1 year won't be the same as next year. MODIS, with its 250 resolution, can provide something which could be crop-specific, but this requires to identify, along the season at least, and where these pixels are, which are the adequate pixels that fall in the field. Now, what's important to think about it here is that you could have representative samples of adequate time series across a region, which is what we're interested in. This could be enough. You don't need to have necessarily a coverage of all fields in the region. If you have a subsample that's representative and that are larger fields, it could be enough. Now, when you have a landscape and you overlay the MODIS L2G grid in which you have the data, the daily data, for instance, many people think that, well, no, maybe I shouldn't say that, but it's a common misconception that perhaps what is inside the pixel is what you think, what the projection of the square on the field. And you would say, oh, nice, here we have a time series that falls nicely in my field. But actually, what is actually in the pixel comes from a region that is not necessarily this grid, that is larger and largely dominated by what is called the point spread function, which is a function that describes how the sensor is capturing information from around the area. So basically, in the center of the observation, there's more response, and as you go further along, the response diminishes. This is a two-dimensional function, even perhaps three-dimensional, if you think about it. So what is inside the pixel doesn't necessarily come from this grid. That's the first point. Now, MODIS is a specific sensor, is a Wicksprung sensor. So basically, it is a cross-track scanner that is scanning the area like that and going back and forth over a large swath. The result is that you have a very high angle from one part of the swath to the other. So the observation away from that increases as you go in the scan direction. This you can think. I have a round something over here, and I try to expand it over there. I'll have a much larger ellipse. And the size of the observation support, where the information comes from, will be increasing a lot. Now, MODIS has a revisit cycle of 16 days. That's one thing. So the angles are changing every 16 days with this pattern. The footprint changes every day during that period. So we're not sampling. Also we have potentially 2 observations per day because we have MODIS Aqua, MODIS Terra passing at different times of the day with different angles, I think. And the idea is that the same area is not sampled in every consecutive day. So the objective of this piece of research has been that to try to exploit this property to identify crop-specific time series from all this. So here, if we imagine 2 pixels here, two time series. This is the grid cell in which we get the data. This is a map. In this case, it's from the cropland data layer of the USDA NAS, and this is a maize or corn field, I think. And this is a soybean field, but it doesn't matter exactly. The point is that this pixel falls in the middle of the field. Here we have another example which falls in between different fields. This is the observation support that you could have for a time 1. This is the observation support that you might have for the time 2. And there for time 3, which has another angle, maybe because this comes from aqua, not terra, and etc. So you see that the information that you get, in this case, always comes from the same land surface. Whereas here we have different land uses. Now, if I have the idea is to estimate the target homogeneity by looking at the observations of NDVI, taking all observations possible, and you can imagine that you presume that a crop-specific grid cell might have a quite coherent time profile to a given extent. It's NDVI, so the BRDF effects are a bit considered. And so it's not so bad of looking at an angle rather than at the top. It still is, you can expect it to be slightly coherent. When you have something in between different land covers, you're sampling different proportion of the different land covers and may end up with something like that. The idea has been to fit something on this curve, and here we fit a cubic spline just for an example, on these curves, and we calculate the percent of noise that we get around this curve compared to the amplitude of the curve. So we get a temporal signal to noise ratio, basically the variance of the signal over the variance of the noise. Well, if you calculate that and spatialize it, you can get a map like that with high signal to noise ratio in blue values, and red is low signal to noise ratio. And this actually reflects the structure of the landscape. This is the same spot in which you have this, I think, this is soybean field, and you have corn over there, which is also represented over there. The areas in between are marked in red. And so this profile actually comes from that pixel. That profile comes from this one, in which you're in the middle of the thing. That means that by just analyzing the signal, the daily observations, and the behavior with different angles, you're actually capable of saying which pixels are convenient to use for monitoring and which are not. Other examples quickly here. Here you have a nice field pixel in the middle of a crop cornfield. You have one in the wheat with a second season. They come out quite well without actual, and you can identify everything that is white over there is quite coherent, and this one is quite bad, and it's quite red over there. By applying this we tested that on an area in the US because we had a nice map of what crop we had over there. Doing an non-supervised classification of the temporal profiles, we see that actually, if we make a clustering with 10 classes, most of the time profiles with high high signal to noise ratio actually have quite a pure amount of crops. I mean, this one is essentially only wheat. That one is a mixture of soybean and corn. This one is essentially corn, etc. And you see, if you see the profile here, you see the median profile of each cluster plus the 5 and 95 percentiles. And you see that they have the behavior that you would expect for different crops. We extended that now to different sites, some of the GECAM sites, which you will hear about probably, if not today, tomorrow or the day after, across the globe, just to see different landscapes with different properties. We took samples of 50 by 50 kilometers, and we calculated the signal to noise ratio over the growing season, what we know would be the growing season, and you can identify already spots over there which generally correspond to different land surface features. For instance, this forest comes out quite well. It's a temperate forest, so you have a signal which is strong. And you can see that if you take here a selection of the purer pixels, you can actually quite well identify winter crops from summer crops, and here, for instance, the forest in the center. This works quite well. For instance, here is in Provincia de Buenos Aires in Argentina, and you have 3 nicely delineated temporal behaviors. You have here South Africa, Ethiopia, and Belgium, just to name a few. Now, an extension to space and time. I did this now over a MODIS style, which is 5,000 by 5,000 kilometers? No, 5,000 by 5,000 pixels of 250 meters. So about, 1,000 kilometers more or less, or something like that, but for 3 years. And this is a color composite in which each color, I coded the signal-to-noise ratio value for each year. So how does it work? Basically, here we have a region in the center of France, a pixel that is green, maybe you don't see it quite well here, but the year 2001 is very coherent, you have a nice signal, whereas the year 2010 is more fuzzy, you probably are in between 2 fields. The year 2012 is something else entirely, and it's not coherent, therefore the pixel is green. Well, here you have a pixel that is magenta. That means that it was coherent in 2012 and 2010, but not in 2011. Basically, with this, you can already see areas where this method will work very well to identify what's happening from other areas where it won't. An example that is quite easy is here in the rice-growing region in Italy, where rice is grown every year in the same place in a very homogeneous way. Everything is white. These white spaces are just artifacts of snow, I think. But this already gives you quite a useful tool to know the limits of where you can use MODIS. We applied it at regional scale, and we can identify the summer crops, winter crops in orange-red colors, summer crops in blue, and forests in green for different regions over this area. And we have a poster on that. So for more details, we can talk later. I would see this as a 3-layer strategy in which we can first focus on the FAPR at 1 kilometer where it works with the method that we had before. We can use this as a second layer to go more crop specific where needed, and perhaps identify the regions in black where to prioritize the use of the coming Sentinel-2 or Landsat time series, in order not to use Landsat or Sentinel-2 over the whole area, because that will be unfeasible for us to manage in a proper way. Now, last point, what to do with this crop-specific signal? Well, part of it, I would first try and construct an archive based on that over the whole MODIS archive, which could, if MODIS goes along for still some time, I think it can still go till 2018 or something like that, we could have a nice reference for regional crop-specific, or we could separate summer and winter crops perhaps, not go crop-specific for everything, but this could help dramatically to use the simple regression technique I was showing before. But also we could imagine better integration of remote sensing with crop models. Well, okay, there's things that we could do using LAI, phenology to recalibrate models. We actually had a try of this a while ago with modest results, but okay, here's a paper just for our info if needed. But something that might be more promising, I think, also operationally, might be to use the fact that we know it's crop specific now. We know we can start thinking about thermal time, the time that the plant is seeing, because the thermal time is crop specific. We had actually a paper also showing how this had some value. I won't go in details because my time is running up, and so I'll skip these last slides about thermal time. But if you want more about that, don't hesitate in talking with me later on. And thermal time, there's different sources. We could better integrate with land surface temperature coming from MODIS or MSG. Conclusion. Crop-specific information can be captured already in many parts of Europe, and it might lead to new avenues to couple better models and modeling and monitoring. But these methods still must be explored, tested, and operationalized with scientific and policymaking community to respond to the demand for a transparent and accurate global agricultural monitoring system. With that, I thank you, and if you have any questions.
Good, thank you. So while we get the next presentation up and shown, then we'll ask for questions. So any questions from Greg?
Have a clarification.
Just wait for the microphone. Some people at the back here. Do you want to put your presentation up, next presentation?
Just want to clarify, the latest Terra review panel puts Terra Motors at least running out of fuel through 2022, and Aqua Motors likely that's for another 4 years we could be on Terra. So you can have another 4 years to that record.
Great. Thanks. Okay. Any other questions?
Nice presentation. Just a quick comment. I was reading in the New Yorker recently, and there's a wonderful article about this computer company in San Francisco that's actually taking real-time data from NextRat and actually coming up with real-time rainfall, water balance, ET, etc. at the farm scale. And I forget the name of the company, but if you look in the New Yorker, it was a fascinating article. And this is all using big data, and it's all computer scientists. They need agriculture